back to quantum mechanics. Today, we will finally be doing the anticipated transformation of quantum mechanics from 1D to 3D. Oh wow, it's actually harder to draw than I expected. I forget how a 3D3 looks on a whim. Alright, so now, as you will probably predict, that gets pretty hard. Now, why is this? I mean, you're only adding 2 more dimensions to an already complicated 2-dimensional system. So how bad can things get? Well, let's start by looking at the Schrödinger equation by itself. Minus I h bar partial t psi. This is in 1D, by the way, but the time term doesn't change anyhow. H bar squared over 2 h bar squared over 2 pi partial x squared psi minus some potential energy function psi. So what's going on here? Well, actually, we already know what's going on here. We've been covering it for a lot of lectures. How does this transform to 3D? Well, the first thing you'll probably notice is that we can no longer use this. That is now the Laplacian. Okay, we'll move to the blackboard. Oh, it's back. This is now instead the Laplacian. But here's the problem. The potential is a very nasty function. Let me give you an example. If I have the gravitational force G m over r squared, the potential is inevitably going to be minus G m over r. But do we even see any components of theta or psi here? If we switch to spherical coordinates, which we need for the radius, do we see any of the other 2 components here? And furthermore, what happens if we translate this to Cartesian? And this is even worse. Well, yeah, you get a square root. Therefore, I mean, a lot of potentials depend solely on radius. But if we choose to go in Cartesian coordinates, all of our potentials, or at least most of our potentials, are going to depend on 3 variables at once. And why is that a bad thing? Well, here's what we want to do.